Welcome today. In our today's recording, we want to look at properties of estimators. The following are the criteria that should be satisfied by a good estimator. Number 1, a good estimator should be unbiased. Number 2, a good estimator should be efficient. Number 3, a good estimator should be consistent. A good estimator should be sufficient. So there's an abbreviation on how to master the 4 properties of an estimator. Call it SECU. S for sufficiency, E for efficiency, C for consistency, and U for unbiasedness. So for easy mastery, we can use the name SECU to master all the 4 properties of estimators. So let's go on. Today, the first video today, we want to look at the unbiased estimator. When do we say an estimator is unbiased? Unbiased for small samples. Definition: an estimator T, which is a function of random sample T, x1, x2 all the way to xn, is said to be unbiased estimator of an unknown parameter theta, if and only if the expected value of T is equal to theta for all theta member of omega. Listen to this. An estimator T, which is a function of a random sample T of x1, x2 all the way to xn, is said to be unbiased estimator for a known parameter theta, if and only if the expected value of T is equal to theta for all theta member of omega. So we have 2 things here. We have the estimator and the parameter. T is the estimator, which is used to predict or to estimate an unknown parameter theta. Let's do if the expected value of T is not equal to theta, we say that T is a biased estimator of theta. If, however, the expected value of T is not equal to theta, we say that T is a biased estimator of theta. In particular, when the expected value of T is greater than theta, then T is positively biased estimator of theta. Moreover, or when expected value of T is less than theta, then T is negatively biased estimator of theta. The expected value of T minus theta is called the amount of bias in T as the estimator of theta. When the expected value of T is not equal to theta, but the value of T is equal to theta, when n tends to infinity, we say that T is asymptotically unbiased estimator of theta. Let's look at an example today. The sample mean x bar is unbiased estimator for the population mean mu, provided the 2 exist. We want to prove that the expected value of x bar is equal to mu, because x bar is the sample mean and mu is the population mean. So for the sample mean to be an unbiased estimator, then the expected value of the x bar should be equal to mu. Then we say the expected value of xi is equal to mu for I is equal to 1, 2, 3 all the way to n, where x1, x2 all the way to xn are random samples taken for a given population with the mean mu. Then the expected value of x bar is equal to the expected value of x1 plus x2 plus all the way to xn divided by n. That's by defining what x bar mean. X bar is the sample mean. You add all the random samples, then you divide by the number of observations. The random samples are x1, x2 all the way to xn. When you put them together, then you divide by n the number of observation, then we say we have our x bar. The expected value of x1, the expected value of x2, plus all the way to expected value of xn is equal to mu plus all the way to plus mu, which is the same as n mu. Then we take n mu